Okay, so the problem that we're looking at here, number 1346, we are going to be looking at the illustration on the left-hand side here. We have a chairlift is desired to transport 1,000 skiers per hour from base position A to the summit at B. The average mass of a skier is 70 kilograms, and the average speed of the lift is 75 meters per minute. Determine A, the average power required, and B, the required capacity of a motor if the mechanical efficiency is 85% and if the 300% overload is to be allowed. Okay. Now, this is a very practical problem. When you design, a lot of times we do design within parameters and kind of thinking about, averages. But as you know, especially when you're dealing with humans and things like lifts or elevators, that's a very variable number. Okay. So you got to kind of plan for what would the extreme be? And that's what they're doing in the second part here. Okay. So we're going to start first by getting what the average power is based on the numbers that they gave us. And then we're going to then build in, some practicality here or some overload situations. So let's kind of get started here. We are going to, this is another practice problem, even though it is a problem out of the problem section. So this is going to be 1346. And this is again on page 828. Okay. Now, this is where we have some power efficiency. So that's why we went over those equations, and you're gonna find that you have a problem or two that's going to relate to this as well. So as we go from A to B, we know that there is going to be about 1,000 skiers per hour. Okay. 1,000 skiers per hour is kind of the rate, if you would. The mass of the individual skiers on average, 70 kilograms. Now they do give us this velocity, but I'm going to tell you, we don't use it. We don't use it. This is one of those problems. It doesn't happen very often, but they give us information that we don't really need. It happens occasionally, right? But I don't know why they even put it in here. So not important. But we're going to find A, the average power required. Okay. And then B, the power at 85% efficiency and 300% overload. Okay. So we'll do part A first, the average power. So the average power, and I'm going to use capital P, is going to be equal to the work from position 1 to 2 or from position A to B divided by the time that it takes to get there. Now, work, as we know, is going to be force times distance, but then we also have the multiplier of the 1,000 because the force that we're going to use is going to be based on the individual skier, but then we're going to have to do 1,000 in an hour. So we're going to start by the 1,000 multiplier, and then we're going to multiply by mass and gravity, and then we're going to put the height that it's going to go. Okay, so the mgh there. This is basically the force times the distance times 1,000 skiers. Does that make sense to everybody? Okay. And then the time that we need to do that in is in 1 hour. So we know underneath here we need to put this in seconds. So that's going to be 3,600 seconds. Okay. So we can fill in our values then to kind of round this out. So this is going to be 1,000 times 70 times 9.81 times the height. Okay. The height we get from the figure. So that's going to be 300 meters. Divided by 3,600 seconds. So our average power, I'm going to put a line over the top. You see that a lot for average. Average power is going to be, should be 57,000, and make sure you check this on your calculator, 57,225 watts. Okay. And a lot of times, thank you, James. And a lot of times we express power in kilowatts. So you could just move that 1, 2, 3 decimal places to the left, and our average power would be 57.2 kilowatts. Okay. And that would be our answer. Whether you express it in watts or kilowatts, same. Okay. All right, so that's the first part. That's our average power, okay? So the second part that we're going to do here is going to be, what is the power at that 85% efficiency and 300% overload, okay? So when we look at maximum power, for instance, we're going to say our power maximum is going to be equal to the percent change, okay, times the average power, okay? So this is why we put percent change on that back side of the equation sheet here, because, or wait, that was at the bottom, because kind of using it for this problem, and they don't give it to you in this particular chapter. So I added this down here. So this is going to be the percent of the amount of power that we're going to use for condition 1 plus the percent of the condition 2. So this would be like 100% power of the average power plus 300%, because we're going to go overload of 300, allow overload of 300, divided by the original percentage, which is going to be 100. Okay. That would be their safety factor. Yeah, saying that there's a 300% overload is a safety factor. Yes, absolutely. It's just a different way of saying it instead of saying safety factor. Safety factor is always usually a direct multiplier. This is looking more at a percent change, right? So we're going to say 100 plus 300 divided by 100 is the percent change in the front of our average power value. So this is going to be the 57.2 kilowatts. Okay. So our max power then that we need is going to be equal to, we should get 228.8 kilowatts. Okay. Now this is not the final answer. This is not the final answer. This is at 100% efficiency that we're putting in, 228.8, and we're getting out 228.8, but that's not realistic. And they said in this problem that, okay, we're going to be at that 300% overload, but now we also have 85% efficiency. So we know that efficiency is equal to power out over power in, okay? So if we know this to be 0.85 is our efficiency, it's going to be equal to, now this is going to be the max power. That would be our power out that we need. So that's going to be the 228.8 divided by the power in, by the power in, P in, that we need to get. So not the one up here, the power in. So our P in, power in, is going to be what we're going to solve for. So P in, it's going to be equal to 228.8 divided by 0.85. So we're going to have to put in 269.2 kilowatts of power to achieve a 300% overload when we're expecting 85% efficiency on our motor. Okay. And then you'll also have a couple of application problems that will, deal with power and efficiency. So I thought this would be a good one for you to, get under your belt to help you with that. All right, so that happens to be the last and final practice problem for module number 4. So I'm going to stop the recording here.